calculations on acids and bases. We're going to review a little bit with the equations, the 4 equations that we're using for acids and bases. And then we're going to do some lab problems. And the basic lab ideas are really, it's called a titration, okay? And they're neutralization. What does that mean to neutralize? If you have an acid and you wanted to neutralize the acid, what would you add to the acid to neutralize it? A base. Awesome. And when you add acid and base together, does anyone remember what 2 people walking into the deli, what you get when you react an acid and a base together? Water and salt. Awesome. I say Walter and Saul. Okay, so it's water and salt are going to be the 2 that you end up getting. So let's go to the notes, and the first thing we're going to do is we're going to write down our 4 equations that we're using. Number 1. The very first equation that we're going to write down is the basic pH plus pOH equation. And if you have pH plus pOH, what does that give you? 14. Now, 14 has no sig figs, okay? When you write down pH and pOH, this is really important, only the numbers after the decimal count. So you would have to write a 0.00 if you wanted 2 sig figs, okay? So just to show you, it's just 14. Okay, that's the way that they define it, because 14 with no sig figs is just an endless amount of sig figs. But if you wanted to do your sig figs only for pH and pOH, only the numbers after the decimal will count. Okay. Second equation. This was derived from the equation of H plus times OH minus. And what is H plus times OH minus equal to? 1 times 10 to the negative 14. Awesome. 1.0 times 10 to the negative 14. And so this actually comes from, the way that they ended up getting this was by negative logging these. And if you negative log the 1 times 10 to the negative 14, you get 14. And so this equation on number 1 was actually derived from number 2. Okay? Third equation is the definition of pH. Everybody, definition of pH is what? Negative log H plus. Awesome. Negative log of H plus. And the last one, number 4, is the pOH equation. And everybody on this one, the definition is negative log OH minus. Awesome. So the thing is, you could have an acid or you could have a base. Okay? If you can figure out your pH, then you can get your pOH. So let's say that you find out how much hydrogen ion you have in a solution. Then that's good, because you can plug that in there, get your pH, and then subtract to find your pOH. Or let's say that you have a base, like sodium hydroxide, or potassium hydroxide, or calcium hydroxide. You could find your OH minus concentration, and then you could negative log that, find your pOH, and then subtract from 14 to find your pH. Okay? So you can really go back and forth. It doesn't matter if you're given an acid or a base. You can still calculate either one. So let's just start off with, what is concentration? We said that concentration was how much solute you have per what? Per solvent, but it's not really solvent. That's not the correct way of defining molarity. It's per what total? Liters total. Awesome. It's your entire solution. Okay? So concentration, in our case, we're going to use molarity. And molarity is equal to the moles, oh, there it is, the moles of solute divided by the liters of solution. Okay, so we're going to call it molarity. So what we're going to do is we want to know what our molarity is in this first problem. And it says that we have 4 moles of calcium chloride and 3.6 liters of water. So how would you calculate the molarity for this? Perfect, just divide. Awesome. So we're going to say that big M is equal to moles over liters. And our moles are 4.00, awesome, divided by our liters, which is the 3.6 liter. And so if you divide, what do you get? Okay, and we have 2 sig figs right there and 3 there. So we want 2 sig figs, so that would be 1.1 molar calcium chloride solution. Okay? Watch what happens next. 3.26 grams of HCl are added to 1.5 liter of water. So now what do we do first? Grams to moles. So we're going to do 3.26 grams of this HCl, throw in a bridge. 35.5 plus the 1 from the hydrogen gives us 36.5 grams per mole. So we L chart it. Okay? And so here we get 3.26 divided by the 36.5, and we want 3 sig figs again. I'm getting 0.0893, yes? 0.0893? Okay, awesome. And that's moles. All right, and this is moles of the HCl. That's not molarity though. So how am I supposed to get the molarity now? Big M is equal to moles over liters. Awesome. So I'm going to take my moles, 0.0893 moles, and divide it by how many liters? The 1.5. Perfect. And so take your answer and just divide it by the 1.5. And I'm getting 0.0595 with 3 sig figs. 0.0595 molar HCl. Okay. HCl is going to break up into what two ions? What will HCl break up into?
H plus and Cl minus.
H plus and Cl minus. Perfect. Okay. So it's going to break up into one H and one Cl. So let's say that I have a beaker of water, and inside of the beaker I place 5 HCl's inside of here. Okay? What's going to happen to the HCl? It's soluble, so it's going to break up, right? It's going to ionize. And how many H's will I have if 5 of these break up?
5.
5. So I've got H plus, H plus, H plus, H plus, H plus. How many Cl minuses will you have if 5 HCl's break up?
106. Never mind.
5. So Cl minus, Cl minus, Cl minus, Cl minus, Cl minus. The reason why I'm showing you this is, if 5 of these break up, you get, as far as your molarity goes, it's the same. You still have a 5 molar H plus concentration, and you have a 5 molar Cl minus concentration. A lot of times people will think that you actually have half. You don't have half. You have 5 H's and 5 Cl minuses. So, if this is 0.0595 molar, then what's the molarity of this one?
0.595.
Perfect. 0.0595. What would the molarity of this one be? 0.0595. Why? Because it's a 1-to-1 ratio. Okay? So because there's one of these for every one of these, and one of these for every one of these, it's going to be the same concentration. This is really important because guess what we need to calculate? pH. Awesome. And we know that the equation for pH is, everybody tell me the definition of pH is? Negative log H plus. So if I know my H plus, I can plug it right into there to get my pH. Okay? And the reason why I showed you this was because a lot of times people will think that it's 2.5, it's half. It's not half. They think 2.5 H plus and 2.5 Cl minus. That's not the case. If you know how many moles per liter you have, it's actually, you look at the ratio from your formula. Okay? So in this case here then, we're just going to plug this in. So my pH is equal to negative log of 0.0595. And so go ahead and type this into your calculator and tell me what you get. Perfect. Okay, let's do sig figs. So this is 3 sig figs. The numbers in pH and POH, only the ones after the decimal count. So I know it's a 1 point what? 225. Good. You have to have 3 numbers because that's 3 numbers. So you have to have 3 after the decimal. The one before the decimal does not count. Again, that's only for pH and POH. Molarity, like we were doing here, is the same as our old rules. Good? So let's do this last one. So our answer would be 1.225, which we would expect it to be acidic because it's a hydrochloric acid. Okay. So now let's try this NaOH one. All right. So we've got, what do I do first with my grams? Convert it. Perfect. So 5.42 grams, and this is NaOH. And so first I need to change grams to moles. And if I add this up, I have 23 and 16 plus another 1. It's going to give me 40.0 grams per mole at 0.136. Nice. Okay, so those are my moles. But I don't want moles. I want molarity. So what do I need to divide by? Liters, nice. But they don't give me liters.
Divide by 1,000.
Good, or take your decimal and move it which direction? If you're getting bigger, your number should get smaller. Good, so we're going to go 1, 2, 3 to the left. Now we're going to divide by our liters, which is 0.300 liters. Okay, so 0.453 if we're doing it this way. And it doesn't really matter. You'll be fine as far as the pH goes, too. Okay, so this is what unit? Mole over liter is called what? Molarity. Awesome. So that's my molarity, and this is of my NaOH. Now, I'm not going to do all of this. What's important in here, in the NaOH? What's going to help me calculate pH? Because they're asking you for the pH. The OH minus. Awesome. This is going to help me calculate my pH. Okay? So, what will this give me, though? It won't give me pH. If I negative log it, what is it going to give me? POH. Awesome. So let's do POH is equal to the negative log of OH minus. And so negative log of this 0.453, which you don't have to show all this work. You can just say POH equals. I'm just doing it for the sake of the notes so that you can see what you did. So in this case, so what do you get when you negative log 0.453?
0.344.
Okay, and we want 3 sig figs still. So again, 3 sig figs after the decimal. So 0.344. Okay, 0.344. And this is our POH. But I didn't want my POH. I wanted the pH. Nice. Awesome. If you go back up to our equations, once you have the pH, then you can always find your POH, just subtract it by subtracting from 14, okay? So if you do 14, pH is equal to 14 minus 0.344, minus my answer, you get 13.66, which is definitely basic. And NaOH should be a base. When you do the pH, it should be greater than 7. Okay, got it? All right, we'll talk about acid rain after too. So let's flip and let's look at the titrations. Okay, so these are all going to be what are called lab questions. So I want to show you real quick here what a titration kind of looks like here. So what you do is you typically will set up what is called a burette and an Erlenmeyer flask will go under it. So you can see there's an Erlenmeyer flask here, and they just have a magnetic stir, so it's supposed to be on this stirring part right here. And then everybody say burette. Burette. Okay. So what you do is you put either the acid or the base inside of the burette, and then inside of here you put what is called an indicator. And indicators change to different colors when they mix with acid and base. So just based, like with the wavelength of the light and the way that it hits it, it'll change colors, okay? Depending on what it's reacting with. And so I had some different indicators here. And so you can see that here, some of them, I put some lemon juice that I had, and I ended up adding some cabbage juice to the lemon juice. The lemon juice was just yellow in water. So it was like a yellowish color. And when I added the cabbage juice, it turned to a pink color. Okay, and in this one, I put some bleach inside of this container with some water in there, and I ended up adding a little bit of the cabbage juice to that one, and that turns more green. Okay, so bases will turn more green, and then the acids will turn more pink, and that's with the cabbage juice. So there are other indicators. Phenolphthalein is something that is used in titrations. It's clear when it's an acid, and then when it's in a base, it actually turns like a bright pink, like a fuchsia pink color. And so I can show you this real quick too. A little bit of ammonia solution inside of here. And so if I just add a drop of this phenolphthalein into it, or a couple drops of this phenolphthalein, you can see that it's turning a pink color, okay? So that's, it turns this pinkish color, and this is used in titrations because what you do is you're waiting for it to neutralize. And so you have acid inside of this flask, for example, and you start dropping the base down. And the base will react with the acid until all of the acid has totally reacted and the base has nothing else to react with. And it's kind of like, I guess if you were like, you know, I love Oreos, totally love Oreos. I'm okay with chocolate chip cookies. But when the Oreos are done, guess what you eat? The chocolate chip cookies. You're like, yeah, I guess I'll go to the chocolate chip cookies, okay? But Oreos are your favorite, right? So the phenolphthalein does the same thing. What ends up happening is the base reacts with the acid until all the acid's gone. Once the acid is gone, the base has nothing else to react with but the phenolphthalein, and then it ends up turning pink. So you'll see that we'll keep on adding base to this, and it won't change colors. You'll see it slightly change colors until the end. So I'll show you this. Okay. So what you basically do is, like in this case, it says select the type of reaction. So I can just do like a strong acid with a strong base. And then you can fill your burette. Typically, what we'll use is we'll use B, base goes in the burette. And then number 3 says select your acid and your base. So the acid that I'm going to select, I'm going to choose hydrochloric acid, and then let's say sodium hydroxide is the base that we're going to use. And you can see that this is starting to fill with the base, and inside of here it's got some acid in there as well. And so that was number 3. Number 4 says select your indicator. And we're going to use phenolphthalein for this, which is the same one that I was just showing you over there. And number 5 says push the slider up to add a volume of base. Okay, and so what we're going to do is we're going to keep on adding. You can either add drops of the base to it, or we can slide this, and then it'll keep on just adding base to it. And what it does is it'll tell you how much base that you're adding. And so you keep on adding the base. Let me come on this side so that you can see this. Did you see how that kind of turned like a little purplish color? And then that's it. Okay, now typically, you wouldn't want to just drop milliliters of it. I'm doing this for the sake of doing this quickly. You would want to then, once you get close and you see that it's starting to turn pink, you want to start adding it drop-wise. And so when you're in the lab, you would slow it down, and you would want someone with patience to do this part. And then you would keep on dropping the base into there until the phenolphthalein ends up reacting with the base and turning it pink. Once you do that, you record the volume of the base that you've added. So in this case, it says that it was 20.52 milliliters. And you compare that to the acid, and you do a proportion or a ratio. What equation did we use for ratios when we did both dilutions, or we did in gas laws, we did one? What did we use? M1V1 equals M2V2. You're going to see that we're going to use the exact same equation for titrations. The only difference is, instead of M1V1 and M2V2, it's going to be MaVa and MbVb. Guess what the A and the B stand for? Acid base. Awesome. And the idea is that once you reach this neutralization point, your moles of both of them are equal to each other. Okay? That's the idea. So let's go back to this. And let's try this. It says, so what is a neutralization reaction? In a neutralization reaction, what ends up happening is your acid and your base react together, and the moles end up being equal to each other. Okay, so you need an acid and a base to produce what? What did we say you produce when you react the acid and the base together? Who are those two guys? Water and salt. Good, water and salt. So a reaction between acid and base to produce water and salt. Now, it doesn't have to be a neutral solution. People will say that it's neutral. Neutralized and neutral do not mean the same thing. If you have a neutralized solution, then your moles are equal. Okay? The moles of both of them are equal. What does it mean to have a neutral solution? If it's neutral, then what about your pH?
Equal.
7. Perfect. Your pH is equal to 7 if it's a neutral solution. If it's neutralized, that's not pH of 7. You can actually have a different pH. Your pH can be 3, and it's neutralized. It depends on how strong your acid and your base are. So, no, they're not the same. Neutralized means that your moles are equal. So titration is the experimental method that's used to find the blank of an acid or the base when you know the blank of the other. What do you think? What do you think we're looking for? Starts with a C.
The concentration?
Concentration. Awesome. the concentration of an acid or a base when you know the concentration of the other. The equipment that's used in the titration, remember the B one? What is that B?
Burette.
The burette, perfect. And I've seen it spelled this way or with the TTE. And what is the other part of the
Magnetic stir.
You need typically you'll use something to stir, but what's the other major piece of equipment? What kind of flask? Starts with an E. Erlenmeyer, nice. The Erlenmeyer flask is typically used. Substances that are used in the titration are the acid, the base, and something else.
The indicator?
The indicator. Awesome. If you don't put the indicator in, you'll never know when it was neutralized, when you reach that neutralization point, okay? So you have to have that indicator there. The indicator changes colors when you have reached what is called the end point, okay? So they call it the end point when the colors change, okay? This is the point where the solution has been neutralized. Awesome. So this means that the blank of acid and base are equal once it's neutralized. What are equal to each other? Moles. Nice. The moles of the acid and the base are equal to each other. And it kind of sounds like equal. They call it, anybody want to guess? EQIV is the beginning of it. Equivalence point. Awesome. They call this the equivalence point. Okay? So the end point is when the color changes. The equivalence point is when they're equal to each other. So see the equation below for proof. So here's the equation. You can see that it looks like M1V1 equals M2V2. Okay? So it's just another ratio or another proportion. Same thing. We're going to use it exactly the same way that we did before. So these problems should be really easy. Watch what happens. Molarity is moles per liter, right? Times what unit of volume should we be using? We said milliliters were okay, but what should we be using? Liters times liters equals MB would be the moles per liter of my base times the volume of my base. What happens? Liters cancel out in both situations. And what you're left with is moles of acid equal to moles of base. Okay? So in a neutralization problem, that's what you're basically trying to get, and that's what this equation will tell you. So if you don't know where it becomes neutralized, you can use this equation to tell you where it's going to be neutralized. Okay? So it says identify the products and write the balanced equations. We did this at the beginning of the year, but so we're coming a little bit back to some of the stuff that we did before. We said an acid and a base will give you water and salt, right? So what are those two? Water plus salt. But let's see what this water and salt actually look like, okay? It doesn't have to be NaCl salt. Water is going to be H2O, okay? So these reactions have two ionic compounds. And I don't know if you remember this. When we had two, we called it double displacement or double dating. And what's going to happen is I'm going to switch these two right here. Okay, you can either switch your positives or you can switch your negatives. So if this goes there and this goes here, what am I going to end up with? K is now with NO3 and H is now with OH. What is HOH? H2O. Perfect. You can write it as HOH because it's usually easier to balance that way, okay? Or you can keep it as H2O. Plus K, which has a plus charge, and nitrate is a negative charge, so it's KNO3, and that one's balanced. Let's try the next one. So now I'm going to switch my H with my Ca. Okay, so these two are going to switch. You know you're going to get what? H2O. Or I'll write it as HOH in this case just to make it easier to balance. So let's make it HOH because I see I have two of the OHs. And what's the other product?
CaCl.
CaCl. Awesome. But calcium has a +2 charge. Chlorine has a -1 charge. So it's CaCl2. Nice. Okay, and then we would balance it. So 1H, 1H, 2 OHs. So I would need a 2 in front of there, which makes it 2 H's, and then I have 2 Cl's and 2 Cl's on the other side. Last one, H2SO4 and NaOH. Again, let's switch the H with the Na. So you're going to switch your positives. And again, we will always get water, which is, yep, HOH, plus, what's the other product going to be? What's our salt in this case?
Sodium sulfate.
Sodium sulfate. Awesome. Sodium has a +1 charge, and sulfate has a -2. Good, just like sulfur does. So this is actually Na2SO4. Perfect. Okay. So let's label these as MaVa or MbVb. All right. And the idea is if it's molarity of an acid, volume of an acid, molarity of a base, or volume of a base is how this is going to work. Is this an acid or a base? Acid. Is that volume or is that molarity?
Volume.
Volume. So you would call this VA. Perfect. Let's try the next one. 3.6 liters of HNO3, acid or base? Acid. Liters would be a volume. So we've got, again, volume of our acid. Obviously, big M makes it. Molarity is NaOH, an acid or a base? Base. So that's going to be our Mb. Okay, next one, H3PO4. That's an acid, and that's molarity, good, of the acid. How about E? Volume, Vb, very good, volume of the base. And the last one? Ma. Awesome, molarity of your acid. So if it has an M, that's your molarity. If it has a volume, then that's going to be your milliliters or liters, that's going to be your volume. Okay. So would you expect to produce a neutralized solution if you mix 45 mils of a 2 molar HCl with 180 mils of a 0.5 molar solution of KOH? If it's neutralized, then what would be true?
Moles are equal.
Moles are equal. Awesome. So I'm going to write MaVa equals MbVb, and what I'm basically trying to figure out is, are they equal to each other? Okay. Let's name these. Let's label all of these. So what is the 45 milliliters representing? VA. Everybody do this with me real quick. What is the molar HCl representing? Ma. What is this 180 mils representing here? VB, because it tells you that that's of the KOH. And so what's this representing? MB. Okay, so let's go back and start right at the back. So what's your MA, please? 2.00 molar. Now, it would be okay even if you wrote it backwards. It's totally fine. Again, with this proportion, you're just multiplying. Okay, coming up, next person. What is your VA, please? Good. 45 mils. Now, typically what you would want in this case, because you want it to equal moles, you'd want to shift your decimal 3 to the left and make it 0.0450 liters. You're going to see that they're going to be, whether or not they're equal, you can figure it out anyway. Equals MB, next person.
0.5.
Nice. And next person for VB.
180.
Good. And then we're going to take that 180 and we're going to shift our decimal 3 loops back again so that it's 0.1800 liters. Okay. Multiply these two together and please tell me what you get when you multiply these two together. 90? 90. 0.1, roughly, moles. Because my moles per liter times liters will give me moles. What if you multiply this together, what do you get? You get?
90, I guess.
90, but that's if we multiply it by milliliters. Yeah. Either way, you're going to see that they're equal. Okay? So whether it's 0.090, in this case it would be 0.090 and 0.090 moles, you can see that they're equal. So is it neutralized?
Yeah.
Yes.
Why did you make it 0.090?
We changed that to liters. So if you multiply the two, then you should get 0.090.
Okay.
All right, and last thing is let's try the problems on here. So you place 20 mils of an unknown NaOH into a flask with a couple drops of indicator. You fill a burette with HCl. So if we were drawing this picture out, it would look like, so you have the base, this is your NaOH inside of here. Then you have a burette. And inside of your burette, you have HCl. Okay, and so what you're going to do is you're going to drop the HCl down in. It says you place 20 mils of the NaOH into the flask. Okay? And then you just fill this with HCl. And you're going to start titrating, and you want to check to see when it ends up changing colors. It says the color of the solution changes, meaning you've reached the what?
Endpoint.
Endpoint. Awesome. It's called the endpoint when the color changes, where it is when the endpoint, when you've reached the endpoint, you can now say that the solution has been neutralized. Awesome. Nice. When you drop 28 mils of the 1.5 into the flask, what is the concentration of the sodium hydroxide? What are we looking for? Concentration of sodium hydroxide. What are the units of concentration? Molarity. Good. And what is sodium hydroxide? The base, right? So that would be your MB that we're looking for. Okay. So this is a titration problem, so what equation should we use? MaVa equals MbVb. Perfect. Okay, so let's fill it in. What's the molarity of the acid? Do we know the molarity of the acid? Yeah, very good. 1.5 m. So 1.50 molar is your acid's concentration. Do we know the volume of the acid? And the acid's what's in the burette. Do we know how much acid it took to neutralize it? 28 milliliters. Awesome. Now again, realize that if you use milliliters here, you're going to get milliliters there. If you were looking for moles, then you would want it in liters. But in this case, we can use milliliters. So 28 milliliters equals. What's the concentration of the base? Well, that's what we're looking for, right? So MB is what we're looking for. And what is the volume of the base that we started with inside of the flask? 20.0 milliliters. Remember, if you're solving for X, you always start where?
The
Opposite side. Good. And you multiply and then divide. Please tell me what you get for MB on this.
2.1.
Awesome. 2.10 molar, and that would be your concentration, in this case, of the NaOH is what we're looking for, of the base. Pretty easy? Okay. Tom and Mark are cleaning the chem supply room, and they found a container that was marked HNO3. They need to find out the concentration, so they decide to perform a titration. Good thinking. They fill a burette with 2.75 molar potassium hydroxide. What is that then? Base. Good. So that's going to be your base. They place 20 milliliters of the HNO3 in a flask. What's that representing? Your VA. Very good. That's the volume of your acid. What is the concentration of the acid? So what are we looking for? MA. Awesome. That's what we're looking for. If it takes 17.4 milliliters of the potassium hydroxide, so that's your V. We know it's a V. Is it VA or is it VB? What's potassium hydroxide? VB. Of the 2.75, we already called that our MB, so we can call it MB again. If you want to, it's the same. The 2.75, 2.75 to neutralize it. Okay, so let's plug it in again. So MA is what we're looking for. Volume of our acid. Yep, 20 milliliters is the volume of our acid. Equals MB. Perfect. 2.75 molar and VB. The 17.4 milliliters. Awesome. Again, where do you start? If you from your X, opposite. Multiply and then divide. And please tell me what you get for MA.
2.39.
2.39. Awesome. 2.39 molar, and this is HNO3. Okay. So, and I've had to do this before, where sometimes the labels on the acids we make solutions, and sometimes they fall off. And so I've had some of my lab assistants actually try to figure out what the concentration is using one that I know. And so that's a good way of doing it. Standardizing a base is finding out what the concentration is of the base by titrating with an acid that you know the exact moles or grams of. Titrations are also used to determine the molecular weight of an unknown acid or base using moles of the acid or the base. Do you remember what the units are for molecular weight? Grams per mole. Awesome. So this is the last type. It says you standardize a solution of NaOH. It's supposed to have a concentration of 0.2. Cross that off. Okay? This happens also. So I prepare the solution. Maybe I prepared it last year. I left it under the hood. I come back this year. I want to make sure that I still have a 0.2 molar solution, because what could happen over a year? Evaporation. And if the water evaporates off, then what happens to the concentration of it? It gets higher. So imagine if you had lemonade or something like that and the water evaporated, it would actually become more concentrated if some of your water evaporates off. So we're saying it's about 0.2, but we want to check to see. So I'm not going to use that in my problem. You place 1.5 grams of some known acid into a flask with about 25 milliliters of water. You cannot use abouts, okay, in your calculations. We need to make sure that we know exactly. We can't use abouts in our calculations. The solution is neutralized, meaning that the indicator turns pink at the end point when you drop 21.52 mils of the base. What is this representing? VB. From the burette into the flask. What is the true concentration of the base? Okay, so what are we looking for? MB. Okay, but this is confusing, because if I go to use MaVa MbVb equation, so the problem is, I don't know this, I don't know this, I'm looking for this, and I know this. Well, that doesn't really help me. But if it's neutralized, then moles of acid equal moles of base. Okay? So if I can figure out the moles of my acid, then I'm all set, because that's equal to the moles of my base. Can I figure out the moles of my acid? What information do they give you? Grams and grams per mole. What can you do if you have grams and grams per mole?
Divide.
You can do a bridge, right? So I know that I have 1.50 grams, and I know the molar mass is 147.5 grams per mole. So that will give me my moles of my acid. So let's divide this. 0.010 what? You need one more number.
0.010.
0.102.
Oh.
These are the moles of the acid, which equals the moles of the base. Okay, again, because it's neutralized, they're equal to each other. So if that's the case, I know the volume of my base, and I know the moles of my base. And what is big M equal to? Moles over liters. So as long as I have MB is equal to the moles of the base and the liters of the base, then my moles of my base are 0.0102 moles, and the liters of my base are what? It's not 21.52. What do you? Yep, 123 to the left. So 0.02152 liters, because you do have to be in liters for molarity. 0.474.
Yeah.
Awesome. 0.474 molar, and that would be the molarity of that. It says next, you place, and this will be the last one that we'll do, you place 1.56 grams of an unknown acid into a new flask with 50 milliliters of water in it. You begin adding the standardized base from above, and the end point is reached when you've added 35.6 mils of the standardized base. So what's that representing? It says of the base, so that would be your VB. That's your VB. What is the molecular weight of the acid? Again, what are the units of molecular weight? Grams per mole. So I'm looking for the grams of the acid and the moles of the acid, okay, specifically. Do you know the grams of the acid?
Yeah.
What is it? 1.56. Right there, it says of an unknown acid. So I know that I'm looking for grams of acid and moles of acid. So I know I have the 1.56 grams of my acid. Now I need to figure out the moles of my acid. Well, the idea is that as long as I know the moles of my base, then they're equal because it's neutralized again. So going back to if it's neutralized, then they're equal. Could you figure out the moles of your base? Well, they only give me VB, but they say that I'm using the same base that I used up here. So that's supposed to be a 0.474. So what can you do to get the moles? Big M is equal to what? Moles over liters. I'm looking for, in this case, the moles, right? So I'm looking for moles. Do I know the molarity of my base?
Yes.
What is it? 0.474 is equal to moles over, do I know how many liters of my base I used? Well, I know milliliters. How can you get liters? Yep, 0.0, so go 3 to the left. So 0.0356 liters. And if you multiply the two of these together, you're going to get your moles. You cross multiply them. And so that ends up equaling 0.0169 moles. Awesome. And this is my moles, in this case, of my base. But it's also equal to the moles of the acid, again, because it's neutralized. So now I'm going to take that number, and that goes right here, 0.0169 moles of acid, and 1.56 divided by the 0.0169? 92.3. Awesome. Grams per mole.